We've talked about limits and how to find limits, how to evaluate limits. We're now going to go back and talk about something called infinite limits. And infinite limits are a little bit different. They require an amendment to the definition. If you recall, we defined the limit to be the number. Well, infinity is not a number, but this is still a helpful concept for us to use in calculus. So let's talk about what we mean here. If a function increases without bound, that means the function just gets larger and larger as x approaches a point. So we're talking about a scenario where we've got a point, let's say this is our point C, and as the function gets closer to that point, it just continues to go up higher and higher and higher. And on both sides, it's going up higher and higher and higher. Then we say that the limit to that is infinity. That just helps us to make some definitions and things that will be easier down the road. Even though infinity is not a number, we say that the limit is infinity as it goes higher and higher. So this is what the graph would look like. If we're actually trying to do this analytically, we're going to see numbers that just continuously get larger and larger as we get closer and closer to C. Well, the opposite of that is a function that decreases without bound. So what would that picture look like? And in that scenario, we've got here's our C point, and the function's getting smaller and smaller. So the function value is going down like this on both sides. Then we would say that this limit is negative infinity. So if the function is getting larger and larger, we say that the limit is positive infinity. If the function is getting smaller and smaller, we say that it's negative infinity. And now notice that in both cases, we do have a point that we're approaching. We're approaching a specific number C. So that's the scenario that we'll be dealing with in this lecture here. A very important thing for you to remember is that limits of infinity or negative infinity lead to vertical asymptotes. So we're going to tie this together with some concepts that we've talked about in previous classes here. So if we say the limit is going to infinity or going to negative infinity from the right or to the left, either one, then that point is a vertical asymptote on the graph of the line, on the graph of the function. So think about that as we move forward here. Determine all vertical asymptotes for each of the following. This is just another way of asking you to find the numbers where the limit equals infinity or negative infinity. Where the limit's either infinity or negative infinity. And another way of asking this same question, which should ring bells from previous classes, when is the denominator equal to 0? So anytime you're asked to find vertical asymptotes, or you're asked to find where the limit is infinity or negative infinity, or the denominator equal to 0, it's the same thing. We're all trying to find the same points. All the same points correspond to these. For examples where we're giving an algebraic problem like these, most of the time it's easier to deal with the denominator being 0. So let's take this first problem. When is this denominator equal to 0? You take the denominator, set it equal to 0, and we find out that it's equal to 0 when x is negative 4. So then we know that we have a vertical asymptote at x equals negative 4. Well, let's also talk about the limit at negative 4. So we're going to look at the limit, and since we know there's a vertical asymptote here, we're going to look at each side of the limit independently. So we're going to say as x approaches negative 4 from the left of f to begin with. Well, what does that mean? We're talking about numbers to the left of negative 4, smaller than negative 4. So let's take an example, maybe negative 4.001. What is the function value at negative 4.001? If we plug that into our function here, we get something that looks like this, 4.001 plus 4. So inside the parentheses here, we're going to get negative 0.001. And now if we multiply that out, we're going to get a negative number, and the magnitude of that number is going to be large. So we'll get something like negative 2,000, I believe is what we'll get, or maybe negative 5,000. So we're getting a number that is very large in magnitude but has a negative sign in front of it. So what does this seem to indicate? Since we know it's a vertical asymptote, we know the denominator is equal to 0, that tells us that the limit either has to be infinity or negative infinity. Since this is a negative number, it's going to be negative infinity. What about if we look at this same function, but the limit as we approach it from the right? So let's look at that. The limit as x approaches negative 4 from the right of f. And you can probably do this in your head. We're talking about a number that's a little bit larger than that. So let's look at let's look at 1 over 2 times negative 3.999 plus 4. Well, when we do the math inside the parentheses, we get 1 over 2 times negative 0.001. It's a positive number now. So this is going to give us the same number in magnitude as the previous problem, except now it's positive. So we can conclude from that that this limit is going to be positive infinity. So we know from looking at this problem that it has a vertical asymptote at x equals negative 4, that from the left this graph is approaching negative infinity, and from the right this graph is approaching positive infinity. So let's take a moment now and let's look at this second problem here. Again, we'll start off looking at where is the denominator equal to 0. Well, we can do that pretty easily. The denominator is equal to 0 at x equals plus and minus 2. And now if we look at the limits at those places, if we look at the limit as x approaches 2 from the left to begin with, all right, what's going to happen there? Well, the numerator is always going to be a positive number, because any number we take and square it and add 4 to it is going to be positive. So we know the numerator is going to be positive. We know we're expecting an answer of infinity or negative infinity. So we really just need to know what's the sign going to be down here. So let's take a number smaller than 2, maybe 1.99. If we take 1.99 and square it on your calculator, you should get a number that's smaller than 4. It'll be a positive number, but it'll be smaller than 4. So we'll have something minus 4. This is going to give us a negative answer. So if we've got a positive number divided by a negative number, it's going to give us a negative answer, which should be negative infinity. What about if we look at it from the right side? As x approaches 2 from the right, again, the numerator is going to be positive. We're talking about a number a little bit larger than 4, 4.01 minus 4. It's going to give us a small number, but a positive number. And positive divided by positive gives us, once again, infinity. Well, what about over here? We don't have a fraction, so we don't have a denominator to deal with. But if we stop and think for a minute, yes, we do. This is the cosine over the sine. That's what this is another way to write the cotangent function, cosine over sine. So we need to know, when is the sine of x equal to 0? Well, if you go back to remembering your trig, the sine is 0 at 0. It's 0 at pi, at 2 pi, at 3 pi, and so forth. So all of these are vertical asymptotes. So we know that if we graph this function, the cotangent function, we have vertical asymptotes at 0, at pi, at 2 pi, and at 3 pi, and the pattern goes on and on just like that. Well, what if we're given a graph to begin with? What can we conclude from this graph? What can you tell me is happening at x equals negative 1 here? Notice we've got a vertical asymptote, so we know we've got limits that are approaching infinity. If we look at it from this side, this limit would be infinity, and this limit would be negative infinity, because this function is going up and this function is going down. So it's important for you to note here now, the limit as x approaches -1 from the right is infinity here. The limit as x approaches 1 from the left is negative infinity. What about the limit as x approaches 1 from the left and right? From the left, it's approaching negative infinity. From the right, it's approaching positive infinity. So it's not approaching the same point. Even though infinity is not a point, it's not approaching the same value, so the limit does not exist. That's an important thing to understand. If we're talking about from the left or from the right, the limit does exist from the left or from the right, but it does not exist for the point as a whole. So if you look at this next graph, the limit at -1, we're approaching infinity on the left side. We're approaching negative infinity on the right side. The limit does not exist. At 1, the limit is negative infinity on the left side. It's positive infinity on the right side. But the overall limit does not exist because it's approaching different points at the left and the right. And with this, again, with this final graph here, you can see that's the one we were dealing with. The cotangent is it's approaching positive infinity on the right side of each of those. It's approaching negative infinity on the left side of each of those. So the limit itself does not exist. So these graphs just go with the problems that we had up at the top of the page there, giving you graphically what it would look like. Determine the vertical asymptotes of the graph. Vertical asymptotes mean denominator equals 0. So that's simply what we want to do. When is the denominator equal to 0? When is x squared minus 9 equal to 0? That occurs when x squared is 9. So x is positive or negative 3. There's really not any calculus to do there except to realize that this also tells us that the limit at 3 and -3 is either going to be infinity or negative infinity. And it may be infinity on one side and negative infinity on another.